Now we are going to discuss about Z transform and its properties. In digital signal processing, most of the places we are using Z transform for the analysis of the digital signals. So first we are going to discuss about the motivation of Z transform. Here the Fourier transform does not converge for all the sequence. Okay, so but at these places we can use the Z transform, and in some analytical problems the Z transform notation will be very convenient as compared to the Fourier transform notation. So these are the main motivation of Z transform. So next one, advantages of Z transform. So with the help of Z transform we can be able to analyze the stability of linear time invariant system. Next one, we can calculate DFT and FT can be determined by using the Z transform. Next we can solve the differential equations by using the Z transform. The differential equations can be solved and simplified with the help of Z transform. So these are the main advantages of Z transform. Now we are going to see the Z transform definition. So the Z transform is a two-sided bilateral Z transform. So that is represented by x of z equal to sigma n equal to minus infinity to plus infinite x of n into z power minus n. So simply we can say x of z. So next one-sided unilateral Z transform. That means x of z equal to sigma n equal to 0 to infinite x of n into z power minus 1. So we can see these two equations. So here bilateral Z transform means the limits n varies from minus infinity to plus infinite. So we have to consider the Z transform for n equal to minus infinity to infinite. For unilateral Z transform, we have to consider x of z equal to sigma n equal to 0 to infinite. So this is the difference between two-sided bilateral Z transform and unilateral Z transform. Next one, region of convergence. So the region of convergence is the range of Z, is the range of values of Z for during this values during this region the Z transform converges. That is the region of convergence. Again we are going to see the properties of Z transform. We have some properties. First one, linearity. Second, time shifting property. Third one, time scaling property. And fourth, differentiation property. Final one is the convolution property. Now let's see the linearity property. So the linearity property states that when two or more individual discrete signals are multiplied by constants, their respective Z transform will also multiplied by the same constant. So here if the individual signals are multiplied by the individual signals are multiplied by constants, their respective Z transform also multiplied by the same constants. So x1 of n tends to x1 of z, like this x2 of n tends to x2 of z. So next we can write a into x1 of n plus b into x2 of n tends to a into x1 of z plus b into x2 of z. Next one, time shifting. So time shifting property says how the change in the time domain in the discrete signal will affect the Z domain. That means this is the discrete signal. So x of n minus n non. That means here we have some changes. We have the change in the time, shifting in the time. So that will be represented, that will be affect the Z domain also. So Z transform of x of n minus n on equal to z power minus n on into x of z. So we are going to see the proof. So here Z transform of x of n minus n on equal to z power minus n sigma n equal to minus infinity to infinite x of n minus n on into z power minus n. Here we are taking m equal to n minus n non. So from this we can calculate n equal to m plus n non. So the sigma m equal to minus infinity to infinite x of m z power minus m into z power minus n non. So from this we can get z power minus n non into x of z, because sigma m equal to minus infinity to infinite x of m into z power minus m, we can write x of z. Okay. So next one, time scaling property. So the time scaling property means here in time scaling property we are multiplying a power n in the time domain. So here x of n changes to x of z. Like this, a power n into x of n means we will get x of z by a. So this is the proof. Okay. Now we are going to see the proof. Z transform of a power n into x of n equal to z transform of n equal to minus infinity to infinite x of n into z power minus n divided by a power minus n. Because here a power n, so we can write z by a into the whole power minus n. Now we will get x of z by a. So here sigma n equal to minus infinity to infinite x of n into, instead of z power minus n we have z by a. So we are writing x of z by a. Next one, differentiation property. So differentiation property shows that z transform will takes place when we differentiate the discrete signal in time domain. So here the z transform of n into x of n equal to minus z into d by dz of x of z. So proof. So for proving the differentiation property, we are differentiating the equation x of z. So d by dz of x of z. So sigma n equal to minus infinity to infinite x of n into d by dz of z power minus n. So we will get z power sigma n equal to minus infinity to infinite minus n into x of n z power minus n minus 1. So we will get minus 1 by z sigma n equal to minus infinity to infinite n x of n into z power minus n. From this we can calculate z power z transform of n into x of n equal to minus z into d by dz of x of z. Again convolution property. So the convolution property means, convolution property says that the z transform of the convolution of two sequence is the product of their respective z transform. So here we have the signal x1 of n is the sequence and x2 of n is the sequence. So the x1 of n z transform will be x1 of z. When x2 of n goes to z transform, x2 of z. So the convolution of these two signals, x1 of n into x2 of n equal to x1 of z into x2 of z. So this is the convolution property. So the convolution of these two signal tends to the product of their respective z transform. Okay, thank you.